Good morning. We will continue with combustion instability. Let us quickly recap where we were last time. See, we talked in terms of let us say a liquid propellant rocket. We told ourselves if by chance the steady pressure in the rocket may be pressure versus time, if it falls in some way and if the pressure drop across the injector is less than some value relating to the chamber pressure, it is always possible for the oscillations to grow with respect to time. We also told ourselves, well, this is something like a diverging and the pressure could reach a level wherein the case may not withstand and it is a problem. And whenever we talk of instability, we mean there is a particular frequency at which the events happen and also maybe the pressure amplitude keeps growing. And how do we represent it? We said to say something is square like this is difficult. Maybe we take a sinusoidal oscillation, and therefore if we have a sinusoidal oscillation we can always say, well, the cycle of oscillation starts here, goes to a maximum, comes back here, starts again. Maybe this is the wavelength of the oscillation. And whenever we talk of a wavelength, that means one cycle of oscillation corresponds to the wavelength and this is lambda. Therefore, we tell that lambda centimeters or lambda meters is equal to your wavelength of your oscillation, and the amplitude of oscillation, the maximum value, is above the mean value, and this level is what we say is the maximum amplitude p hat. If I have to show this cycle of oscillations, well, I say it could be something like a sin theta or a cos theta, and therefore I can write the oscillation at any particular point. Let us say over here I say it is p prime, maybe over here it is p prime. I can always write it in the form maybe a maximum value into something like cos omega t or sin omega t, right, because I presume that this square one which I show as a Tc could have been represented something like this, going like this, because nothing is going to be sharp in nature, and therefore if I were to show it as cos theta and sin theta, I can always represent it by e to the power I omega t, right, where now omega becomes something like the frequency of the oscillation. How do I define frequency? I have a wavelength lambda, and if my wave is travelling at a speed a, then the time of one oscillation is equal to, I have time of an oscillation is equal to the wavelength divided by the speed of sound, namely I have meters divided by meter per second, that is the wavelength, and therefore I tell myself this lambda corresponds to a time t, right. And therefore what is the frequency of oscillation? Frequency is equal to 1 over time, so many cycles per second, or this is equal to a by lambda. Or if I were to put the frequency in terms of radians per second, I say omega is equal to 2 pi into f, so much radians per second. How do I now show the pressure amplitude? In terms of both frequency and in terms of let us say this value here now when I say omega now refers to so much radians per second, and I say the value is p prime is equal to p hat, which is the maximum amplitude e to the power I omega t. I also wanted to tell how whether the oscillations are going to grow with respect to time. If it is growing, the value of the p hat will keep growing. In other words, it grows with respect to time, and therefore I add one more term and tell that p hat or p prime can be written as some value, some nominal value into e to the power alpha plus I omega into t, where alpha shows you the rate at which the oscillations keep growing. And if now I say if alpha is greater than 0, it means that the oscillations keep growing with time, and the system is unstable. If alpha is equal to 0, what does it mean? The oscillations are steady, there is no question of whatever be the peak it keeps going, it is something like neutral, or we say it is a limit cycle oscillation, right. It goes into a limit cycle mode, it keeps oscillating at the same amplitude. If alpha is less than 0, all what it says is I start with an amplitude, it keeps decreasing with amplitude, and therefore alpha less than 0 means it is a stable system. Therefore, we had defined alpha as the growth rate of the oscillation, and what will be the unit of growth rate? Well, I have t over here, therefore, if I were to take the logarithm of both sides, I have ln p prime is equal to ln p into alpha t, therefore, I have 1 over second must be the unit of growth rate. Let us put it together. I want the unit at which the waves grow. I have ln of p prime is equal to ln of p hat, and therefore, and then I get alpha plus I omega into t, because ln of E is 1, and therefore, the unit of growth rate should be 1 over second, because this is ln p minus ln p, therefore, I can take it as ln p prime minus ln of well, the ln p prime minus ln p I can write as ln of p prime by p hat, and therefore, alpha should have unit of 1 over second, and anyway frequency also has units of radians per second over here, and this is the way we normally show the oscillations. We also talked of one more thing which was fairly important. We told that in some cases when we considered this particular rocket chamber, we never really differentiated the pressure at this point from the pressure at this point. We told ourselves a liquid fuel is injected, it gasifies and produces hot gases and mixes, burns and all that, and the pressure in the entire chamber is the same throughout. But we also know if I were to create a disturbance at this particular point, the disturbance should travel with respect to time, and therefore, the pressure here, if I were to write as Px over T, should be different from a pressure at this particular point, maybe Pxt, let us say P prime is the disturbance what we are getting, it will be different at the different locations x, where x could be a vector, maybe it could be along the axis, it could be anything. As the position changes, maybe my pressure should change, provided the waves are traveling in this. When we considered the question of injector and something being built up, we assumed that the entire bulk of the oscillations or bulk of the chamber oscillates in unison. That means whatever be the pressure here is the pressure here is the pressure here, and this is valid only under certain conditions which we have to see. Why did we make these assumptions? Therefore, we talked of bulk oscillations. What did we mean by bulk? The entire mass of gas in the chamber is as if it were at a point, that means a lumped mass assumption, and we lump all the things together and we call it as a bulk oscillation. And for this we developed a theory based on TC, and we were able to explain under what conditions in a liquid propellant rocket and in a solid propellant rocket we can get oscillations to happen, and these oscillations could grow, right. Having said that, we also came to the question of supposing I have a wave, how do I describe a wave, and what did we get at? We said, well, I could have a wave, and the wave, an acoustic wave, let us consider. Maybe what are the different types of waves? We can talk in terms of an electromagnetic wave, an acoustic wave, a shock wave, maybe a blast wave. Maybe we will have to look at some of these waves. When I say an acoustic wave, we mean something like a sound wave, and that is how a disturbance propagates. I make some noise and it comes to you. Therefore, what is it I am talking of? Maybe I make some disturbance, and how does the disturbance comes to you? Maybe it compresses the medium, my vocal cord compresses, then it releases, then again it compresses, again it releases the medium. That means we can represent it as a series of compressions followed by rarefaction, followed by compression. That is how a wave travels, and it travels, a sound wave travels at a speed a meters per second. Under room temperature conditions, room pressure conditions, we know that the sound speed is around 330 meters per second, but it need not be the same speed in a chamber, we will have to see that. Therefore, all what we said is, well, if it is going to travel as compression and rarefaction, that means I have a compression over here, followed by expansion, followed by compression, followed by expansion. I can as well show a compression something like this, a rarefaction like this, and therefore, a wave can be schematically shown as a compression followed by expansion, and this is the way a wave travels, and therefore, this is x and this is your value of p prime. Now, we wanted an equation to this, and we told yes, this point and this point are in the same phase. I can show this by wavelength lambda, and a wave which consists of compression and rarefaction can be described by the equation. Let us write an equation for this. We say x is the distance along the direction of propagation. We say p prime is equal to the amplitude. This amplitude, I call it as a is the amplitude, and it is a single wavelet I am taking, a into sine of, and how do I say sine of? This corresponds to 2 pi corresponding to lambda, and I want to find out the amplitude at x. Therefore, maybe x by lambda is what gives me a particular position. Therefore, I say 2 pi by lambda into x is the equation to this. But we also said that this wave is apparently travelling, and therefore, if it were to travel at a speed a, as we said, at a time t, the wave should have travelled a distance x is equal to at, and therefore, at time t it would have come over here, and therefore, the wave is now at this position, and this distance what has travelled is equal to at. Therefore, the equation to this travelling wave, that means it is travelling. Therefore, if I want at any x here, I have to subtract the value of at over here, and therefore, the equation to a travelling wave therefore become a sine of 2 pi by lambda into x minus at over here, right. This is what we wrote. Now, we want to simplify the whole thing again and put this equation in a slightly simpler form, such that it is more amenable to some analysis, and therefore, I can always say 2 pi by lambda is what we call as a wave number, and this I call as k, capital K. Capital K tells the wave number, and that wave number is defined as 2 pi by lambda. And we also, just some time back, we said that the frequency of oscillations is written as 2 pi into a by lambda. We define the value of time t as lambda by a, capital time t for one oscillation. Therefore, frequency is lambda by a by lambda, and therefore, omega is equal to 2 pi a by lambda. Now, I substitute these two into this equation, and I get the oscillation p prime. I made a correction over here, p to p prime is equal to a sine of 2 pi by lambda into x minus 2 pi by lambda into at over here. Therefore, now I know the wave number is 2 pi by lambda, I can write it as a sine kx, and 2 pi a by lambda is equal to omega, and therefore, the equation to the wave which is travelling, like what I am rubbing out, I showed a travelling wave, is equal to p prime is equal to a sine of kx minus omega t, right. Let us remember this form, because k is the wave number goes inversely as lambda, 2 pi by lambda is known as a wave number, and omega is the frequency what we have. We are interested in the frequency of oscillations, we are interested in the wave number, and therefore, we can write it in this particular form, right. Now, I consider the wave is travelling let us say a tube. Let us assume that the tube is closed at both ends, the wave is travelling forward, this is the way it is travelling, the wave comes and hits a solid surface here, and let us say there is no attenuation of the wave does not lose any energy, it is reflected back and comes over here. Now, when it is reflected back, the same wave, it is travelling in the opposite direction x, therefore, the equation to the reflected wave should be equal to a sine of minus kx minus omega t, right, and therefore, this becomes equal to minus a sine of kx plus omega t. Now, we want to find out, see, after all, a rocket chamber, we have been repeatedly telling that a chamber consists of something like a hole, a cavity, and what does the cavity consist of? Here it is blocked, here you have the injector, nothing can go in this direction, and you have the nozzle in which high velocity gases are flowing, the throat is sonic, Mach is equal to 1, and whenever we plotted the density variations and pressure variations in the nozzle, we found that the density keeps decreasing, it becomes very rapid at the throat, and therefore, there is very rapid change in density at the throat, therefore, this is as good as a solid surface. There are so much changes taking place in the throat region that it behaves something like a solid surface itself. There are so much changes in density that the wave, when it sees it like a solid surface, and therefore, it reflects back. Therefore, the chamber of any rocket chamber is like a cavity closed at both ends. Now, you have a wave which is travelling forward, and the forward travelling wave is given by a sine kx minus omega t, the reflected one is given by minus a sine omega t, and therefore, you have these periodic disturbances which are created, therefore, the waves are travelling forward and the waves are coming back, there is interaction between these waves which are going like this and the ones which are reflecting, and the net wave what we get is a combination of the incident and the reflected waves. Therefore, I can now write P, which is the resultant wave, is equal to the incident wave plus the reflected wave. Incident wave is P prime, let us say the resultant fluctuation is equal to sine kx minus omega t. Now, plus I have P prime, or let us keep the same notation, A sine kx minus omega t, and the reflected one we just now see is equal to minus A sine kx, therefore, it is equal to minus A sine kx plus omega t. This is the resultant. If this is the resultant, let us try to solve this. Sin kx minus omega t is equal to sin kx cos omega t minus sin minus cos kx into sin omega t, and since I have a and a is for the first term, the second term becomes minus a sin kx into cos omega t, and now I have plus here, therefore, it is minus a cos kx into sin omega t, and therefore, I add these two things together, I find this term drops off, and therefore, the resultant wave is equal to the value of minus 2a into cos kx, that is wave number, into sin omega t is the resultant wave. Therefore, what has happened? I had a series of waves going like this, it bounced back, came like this, and the net effect of this and this put together is the resultant wave. And now, when I look at this, I have some strange things happening. The wave was travelling with a speed a, now I do not have anything travelling, and what is it, what is this which is getting reflected here? Let us ponder on this resultant wave for a couple of minutes. Let us see what is happening. Now, what does this represent? Maybe at some location x, where cos kx gives me the magnitude of 2a cos kx, I have p prime which is this, or rather if I were to say, well, my chamber, which now I say is as good as a closed cavity, and this closed cavity is of length L. All what I am trying to say is, maybe at this point x is equal to 0, I have cos kx which is 1, I have minus 2a, that is 2a sin omega t, but that means the amplitude of oscillations here is quite large. Maybe it oscillates like this is my time axis, and the frequency of oscillation is given by omega. Maybe at some other location x where x is not equal to 0, I have the cos kx which is less than 1, the magnitude maybe at some other location over here. Maybe what is going to happen is, this is the value, this is the value of 2a what I had, and now this is going to be much lower, smaller magnitude. My amplitude will come down, and I have the oscillations at the same frequency omega, but my magnitude gets changed. Over here maybe the magnitude may be still smaller, I have to find out, but my frequency will be the same, and therefore what is it I get? I get at fixed points oscillations of a certain amplitude, and these are not travelling anymore. That means the combination of the incident wave and the reflected wave leads to something like a standing or a stationary wave, which no longer travels. Therefore, what is going to happen to my combustion chamber? My poor combustion chamber, if the waves are travelling forward and backward, at some point I will have a value of p prime, at another point I will have a smaller value of p prime, maybe at second, third point I may still get maybe a still different value of p prime. This p prime is oscillating at some frequency, it is also oscillating at the same frequency, only the amplitude is different. Here maybe the amplitude may be so small that it is like this, therefore different points have different pressures in this. But each point has a particular thing, things are not travelling behind it. That means it becomes a standing wave, and therefore the combination of the incident wave and reflected wave leads to a standing wave, and the characteristics of the standing wave are such, at a given location the amplitude remains the same throughout the period, at different locations the amplitude changes, but at a given point the amplitude is same. Whereas if I talk in terms of a travelling wave, what is the equation to an incident wave? P incident p prime we said is equal to a sin 2 pi by lambda into x minus at, and what is going to happen to a travelling wave? Maybe the point is here, the point sees the maximum amplitude a, then it sees a slightly smaller amplitude, then it sees a negative amplitude, then it sees a positive amplitude, whereas when the combination of this at a particular point I get the same value, the amplitude does not change at all, and this is important. In a wave in a cavity, because you have forward and backward waves which are interacting, you are led to a standing wave or a stationary wave, and the frequency at the different points remains the same, but the amplitude at the different points are different. Is this clear? If this is clear, I can now calculate the frequency. And how do I calculate the frequency of the wave? Well, I have the equation to the net wave, and the equation to the net wave, let us write it again. P is equal to minus 2a, and this is equal to cos kx into sin omega t, omega is the frequency. I want to calculate the frequency, therefore I again maybe make the same plot again. Well, this is my cavity, I have simplified my cavity as a cylinder of length L, let us say, and my wave is travelling in this particular direction, it interacts, and therefore I now form a standing wave. And now what is going to happen? I take this particular term, I tell myself this is a closed end. At a closed end the velocity perturbation should be 0 because it is a solid surface. If velocity is 0, the pressure should be a maximum, and therefore the value of cos kx should be equal to 1 at this end and at this end. At this end, the moment I put x is equal to 0, indeed it is satisfied. At this end also it is a closed end, therefore I say cos kl is equal to 1. If cos kl is equal to 1, kl is equal to n pi, where n could be maybe 1, 2, 3, 4 and so on, because we have no control, it could be 180, it could be 360, it could be any number. And therefore, if KL is n pi, and what was K wave number was equal to 2 pi by lambda into L is equal to n pi, and therefore we can now simplify this equation to read as lambda is equal to, let us put it together, lambda comes on top over here, and therefore you have 2 pi L divided by n pi is the value of lambda. And what is the frequency omega is equal to, let us put it together, what was A by lambda, or frequency, let us put it as frequency itself, why carry f over here, frequency is equal to A by the lambda, sound speed by the wavelength, that is distance travelled in one wavelength, and therefore this becomes equal to, if we were to substitute the value, I get the value A into n pi divided by 2 pi L, which is equal to pi and pi get cancelled, I have Na by 2L is the frequency. Let's sort of internalize this a little bit by working an example. Supposing I have a chamber of length, let us say half a meter, and half a meter looks to me to be reasonable, that is the length of the chamber is 0.5 meters, and the velocity of sound in the chamber is, let us say 1000 meters per second. Why did I write 1000 meters per second? The velocity of sound A goes as gamma RT under root, I think all of you would have derived it, A square equal to under root dP by d rho, and therefore this becomes gamma RT, and temperature in the chamber is quite high, of the order of some 30,000, 3600 Kelvin. The ambient temperature at which it is 330 meters per second is of the order of 330 meters per second at a temperature around, let us say 30 degrees centigrade. And therefore, if I take the mean temperature in the chamber to be something like 3000 into 36,000, 3000, and if I take the ambient temperature as 300 Kelvin, well, I get the speed of sound to be much higher, maybe under root 10 of 338, and this gives me around 1000 meters per second. I just take a number, it could be between 900 to 1200, and therefore, what is the typical value of frequency? For n is equal to 1, we have the frequency as equal to Na by 2L, and in this case I have n is equal to 1, that means fundamental, A is 1000, 1 is 1000, 1000 divided by 1, which is equal to 1000 hertz or 1000 cycles per second. This is the frequency in the fundamental, and now if you are looking at the wave structure, the way the waves are formed, well, at the point over here, that is on the left hand side, well, it is a pressure antinode. At the nozzle portion where you have steep gradients, it is again a pressure antinode. Therefore, I have large oscillations over here. I have similarly large magnitude oscillations over here, and in between at the center I have a node. In other words, the oscillations are maximum on the left hand side and over here, or rather the value, that means I have oscillations which are of this magnitude over here. Similarly, on the right hand side I have oscillations of this magnitude over here, and now the oscillations keep decreasing until at the pressure node the oscillation is 0. I have therefore the waveform like this. In other words, all what I am trying to say is, on the left hand side wherein you have a pressure antinode, the oscillations are like this of large magnitude. The oscillations here in pressure are 0 being a node, and over here the oscillations will be of exactly the same amplitude, but of a different phase. Rather, now I will get the value coming out to be here, if it is positive, here it will be negative, and therefore the oscillations are like this. Therefore, at the fundamental, you have large oscillations in the amplitude of the pressure at the antinode regions, and therefore what is it we also find over here? When the oscillation in amplitude p bar is maximum and it is positive in this case, the amplitude of oscillations leaving the nozzle is negative, and therefore the thrust of a rocket motor depends on the pressure at the nozzle, and therefore the thrust oscillations could be out of phase with the pressure oscillations as you are measuring at the head end of a rocket motor. You know, our aim was to find out the frequencies for the different cases, and therefore now if I consider n is equal to 2, the frequency is equal to now 2 into 1000, 2 into 1000, that is 2000 cycles per second or 2000 hertz. And what will be the type of the wave structure what I get? Well, I have something like an antinode here, I had at the nozzle an antinode over here. In the first case I just had these points over here, that means this was my waveform at n is equal to 1. Now what I start getting is, now I start getting a node here, I get an antinode over here, I get a node here, and therefore my magnitude of oscillations will go like this, come back over here, go over here, come over here, go over here, again come back to this. In other words, I have n is equal to 2, which gives me 2000. In this case my pressure node corresponding to n is equal to 1 now becomes my pressure antinode, and this is my magnitude of oscillations, the frequency is 1000. When I have n is equal to 3, well again I need to have maximum pressure over here. In other words, I need to get one more waveform. In other words, I come over here, this again becomes my node here, I start getting more waveforms. In other words, I get something like this, coming back over here, coming over here, coming over here, coming over here, and similarly the waveform goes like this and so on for different values. Now n is equal to 3 gives me a frequency of 3000, and what is it I observe in all these cases? What I observe is I get discrete frequencies corresponding to frequencies as a case of pressure amplitudes. Let me plot the maximum pressure amplitude at the antinode portion. I get at 1000 hertz, then again I get at 2000, I get at 3000, I get at 4000, and so on. These are the discrete frequencies at which I get pressure oscillations. Maybe this is my magnitude here, maybe this might be my magnitude here, this might be my magnitude here, therefore I get oscillations like this. And what is important to note is only at these discrete frequencies of let us say 1000, 2000, 3000 and 4000 hertz I get amplitudes, and in between these frequencies, in between the frequencies between 0 and 1000 or 1000 and 2000, there are no oscillations at all. It is all discrete at these particular values of frequencies. We call n is equal to 1 as fundamental and n is greater than 1, 2, 3, 4 as harmonics. N is equal to 2 is the first harmonic, n is equal to 3 is the second harmonic, and n is equal to 4 over here, that is 2, 3, 4, 4 is the third harmonic, first harmonic, second harmonic and third harmonic. Now the question comes, we also told, why should there be only pressure oscillations? It is also possible to get velocity oscillations. After all, in a chamber I am getting flow. I also told this is closed end, therefore the velocity here, velocity perturbation is 0. How do I calculate the velocity perturbation from the pressure perturbation? Well, I use my momentum equation, and what is my momentum equation? Rate of change of momentum by Newton's second law. Rate of change of momentum is equal to the impressed force, and now I therefore write dV by dt is equal to minus the pressure difference. What is this? Mass into acceleration. Therefore, if I have a distance dx, well I have dx over here, dx into a dx, and area combines over here, and therefore I brought dx down, therefore this is there, and now I have the total mass is rho dx, therefore 1 over rho, this is my momentum equation. What is momentum equation? dV by dt is equal to minus 1 over rho dp by dx, and instead of looking at it, let us just say mass into acceleration is equal to the impressed force, and rho dx into a is the mass, and I have minus dp coming over here, and therefore this is my momentum equation. What was my value of pressure? Let us say my velocity perturbation, my pressure perturbation over here. Therefore, but my pressure perturbation was equal to minus 2 cos kx into sin omega t. We have derived this. This was 2a. This was my pressure perturbation. How did this come? It came from the incident and reflected, and this is my value. I want to find out my velocity perturbation. Therefore, I differentiate it with respect to x. I get the value of dp prime, let us say by dx is therefore equal to plus 2 k sin kx into sin omega t, and now I have to get the value of v prime, and this is equal to divided by rho is equal to the value of dv prime by dt, 2k sin kx by rho into sin omega t. And now if I were to integrate with respect to time, and I take all the constants including 2k by rho, and now I will get divided by omega when I integrate it with respect to time, I get something like b into some value, let us say sin kx into cos omega t, and now I find that now I get cos omega t, whereas my basic pressure signal was sin omega t, my velocity signal v prime is sin omega t, and therefore I can write this as b sin kx into sin of omega t minus pi by 2. In other words, the velocity perturbations lag behind the pressure perturbations by pi by 2 degrees, and therefore I can now plot, since it is lagging behind, for the same case if I were to plot my velocity perturbations, I show it on the top, lags by 90 degrees, I get velocity 0 here, velocity node here, velocity node maximum, and I get my velocity perturbations like this. So also I can keep plotting wherever I have a pressure perturbation or pressure antinode, I get a velocity node, wherever I get a pressure node, I get a velocity antinode, and this becomes my velocity perturbation. This is all about standing waves, but standing waves are important because they tell you at a particular location in the chamber I know what is the value of the p prime, and therefore it is possible for me to get the fluctuations. If this part is clear, let us put the composite whatever we studied earlier and today what we studied for standing wave together. What is it we are telling? Supposing I have a chamber and this is the length of my chamber. If I have a wave of very long wavelength, what is it I am saying? Well, my distance is x, my wavelength is very long. In other words, the wavelength is so long that now I get a wave like this, and now because the wavelength is so long that there is not materially much difference in the pressure perturbations, that means compared to the length of the chamber, if my lambda wavelength is going to be very much larger than the length of the chamber, well, my value of p xt need not be a function of this. If it is very much longer, maybe it is going to go like this and come over here. That means the pressure in the chamber can be very small, or rather the bulk mode of oscillations corresponds to the condition when the length of the chamber is, when the wavelength is so large that my length of the chamber is very much shorter than the wavelength, or rather I can assume the value of p xt for all x to be same as pt, or rather the bulk mode of oscillations will happen only for large wavelength, that means very low frequencies. Therefore, whatever we studied for bulk mode of oscillations coming from the injector or from a solid propellant from the response of the surface, giving you the oscillation wherein you brought down the pressure, again it went up, it went off, and then again it came down like this, again it went off, again it came down. These have to be essentially at low frequencies. Therefore, L star oscillations which we studied yesterday are essentially low frequency oscillations, and the wave mode of oscillations must essentially be at higher frequencies. I think this part must be clear to each one of us. Okay. Let us now go forward. Let us try to understand a little bit more of what we wanted to study further in this. If this part is clear, I ask myself one question. We have still not addressed the total point when we had the flute and we said it makes some noise. Why did the noise come? Therefore, I want us to be very clear about it. Let us say this is the particular flute what we had. We said this is the length of the chamber. We had a small hole at the point where we are injecting. Let us again draw this figure over here. I blow air over here, I allow it to come, I had a small hole over here, and then I have the chamber. We also have, for musical purposes, different frequencies. I have a series of holes here, and this end was open. I now close this end. I have a closed end here, I blow air here, still it makes noise. But if I were to plug this hole, which essentially generates the disturbances, I blow, it does not make noise. In other words, the disturbances which are created here because of this and interaction with this goes forward, gets reflected at the open end, travels back, forms a standing wave, and this standing wave gets modulated by these things. If I open it, maybe my length gets decreased, therefore my frequency gets changed, I have a higher frequency, and then I keep playing with the frequencies by opening this, and I can play music. And this is essentially what is happening in a rocket chamber also when I have instability problem. I have the chamber like this, I have the nozzle over here, maybe I could get combustion taking place here, the combustion interacts with the pressure mode here, increasing my amplitude of pressure at this point, and my whole amplitude, the standing wave amplitude increases, and therefore my pressure increases, and therefore maybe with respect to pressure and time, maybe I start with here a small oscillations, it grows faster and it creates a problem for me, I end up with very high pressure. And this is what we mean by combustion instability, and combustion instability happens in the standing wave mode, and it is known as a wave mode of combustion instability. Therefore, let us now put together the points what we have studied so far together. We tell ourselves, well, combustion instability could happen either in the bulk mode of oscillations, and these bulk mode of oscillations are essentially low frequencies. Why is it low frequency? Because all points have the same pressure, or rather lambda is very much greater than the characteristic length over here. Or it could also happen in the wave mode. We are still to write an equation and find out what happens in the wave mode, but we recognize in the wave mode the frequencies lambda is going to be comparable with length, if not going to be less than the length, and this happens essentially at higher frequencies. Therefore, we say that, well, injector induced oscillations or the feed system induced oscillations are essentially low frequency oscillations, or because of the heating of the propellant and low L star values, I have low frequency oscillations, whereas for wave mode that need not be true. I can have any standing wave and it would create oscillations at higher frequencies. I think this part must be clear. See, yesterday I also showed you the figure of a whistle. The whistle was not long. What was the construction of a whistle? Same thing over here, a hole over here. I had a chamber over here, but then here the motion was not in this direction, motion was in this direction. It could have been oscillating in the tangential mode, it could be going in the radial mode, but we have not, we have all what we have studied is something going up and down over here. We have studied only in terms of the axial oscillations. And let us say in a rocket chamber, supposing I have, let's again plot it out and see. In a rocket chamber, it is also possible for us with cylindrical in shape, any cross section I take is a circle. It is also possible for waves to go in this direction up and down and form a standing wave in the axial direction. It is also possible that the wave goes in the circumferential direction, which we say is tangential. Why tangential? I have a center, it could go in the radial direction, therefore I could have oscillations in the radial direction, and therefore my problem becomes even more complicated. That means I could have oscillations in the radial and tangential direction, just like in a whistle. I have a small thing, but still it made a shrill sound. That means oscillations, I induce disturbances, the disturbances travel in the tangential and radial modes, and I get that shrill sound of a whistle. So also I could get tangential and radial modes in a chamber. How do I solve for the tangential and radial modes? Well, it is a little more complicated. I cannot write these simple equations because axial. I could readily write maybe P prime is equal to A into sine of 2 pi by lambda into x minus 80 for the forward wave from which we derived the equation. It becomes a little more complicated. I have to go back to my basic wave equation. And what is the wave equation? I have d squared p prime by dt square for a one dimensional axial wave is equal to a square into d squared p prime by dx square. Let us see if it is clear. A square is meter square by second square, meter square over here, t square over here. Well, this is my wave equation, but if it is going to be in the other directions, I have to change this equation to read d squared p prime by dt square is equal to a square into I have nabla squared p, where nabla squared is equal to maybe 1 over r. I have dr by dt if it is cylindrical, d 1 over r into the value of dp by dp prime by dr, plus I have 1 over r squared into d squared p by dr square, plus I have the value of d squared p by d theta square, where again the value of something like 1 over r square will come, and therefore it becomes a little more complicated, but I can readily solve it using the method of separation of variables. Maybe you all should do it, and when I do it I can find out the modes of oscillation in tangential and in radial modes, right. And now I show this on a PowerPoint because I did not want to solve this. Let us go back, just quickly revise through what we have done and where we are now. What did we tell? Let us see with something what we know already. We said the reflection of a incident wave from the solid body creates a standing wave. You have pressure antinodes at the ends which are closed and a pressure node at the center. This is the magnitude of the oscillations 2a, and this is the value of frequency, and frequency is equal to a by 2l. When I go to the first harmonic, that is n is equal to 2, well, I have antinodes here, I have another antinode at the center, I have nodes over here. This is the shape of my wave which is going. When I go to the third harmonic, that is second harmonic, that is I put n is equal to 3, well, I get another series of maximum pressure here, antinode, 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 and 2 nodes over here. If now I were to put the velocity together, well, at the region of pressure antinode here I get a node in the fundamental, I get an antinode here, then in the first harmonic, which is n is equal to 2, I get antinode, antinode, a node here, node here, node here. Well, in the next harmonic I get the value, I have something like 1, 2, 3, 4 nodes and 3 antinodes, and therefore at these points wherein I have velocity antinode, maybe a momentum could increase the velocity. We will look at it at the next class, and therefore now I ask myself what happens in the tangential. By this particular diagram I need to qualify it a little bit. What is it I am talking of? I am talking of a diameter and now I get oscillations in this particular direction. The first node or the first mode of oscillation is maybe I have an antinode here, I have an antinode here, it goes like this, and this is what I represent here. I have maximum pressure oscillations here at one time, maybe at the next instant of time I have here, therefore I have it is oscillating in the tangential direction. Maybe when I go to the second mode, well, I have two more places where I have the maximum pressure, therefore two more places where I have this, and now I have this and this, and I find that the value here shows the value of P prime, that is the local value divided by the maximum value which is possible, and this is a non-dimensional pressure amplitude, and this is with respect to radius. I just want you to appreciate the complexity. This is all done by solving this equation, and the figures are shown using MATLAB plots. And now if you say in the third mode, well, I have places wherein I have maybe maximum pressure oscillations at the edges 1, 2, 3, 4, 5, 6 over here, and it is still oscillating. You see the red one shows maximum pressure, the green one show negative pressures, and in between I have variation of pressure. And similarly in the radial mode, well, at the wall I have maximum pressure, at the center I have minimum pressure, negative pressure, at the next instant of time I have minimum pressure here, maximum pressure here, and therefore this is the way I get antinode here, antinode at the wall region, antinode at the center. Second radial mode, well, you see outer I have one, at the middle of this around 0.6 of the radius I have another antinode, maybe at the center I have another antinode. You see the magnitude of pressure oscillations at the center is much higher than at the walls, whereas when we looked at the tangential modes, you got just the opposite. You had higher values at the wall and lower at the center, and therefore if you were to couple, after all these are all oscillating together, it is always possible that some of the radial modes will get coupled with this. And how does it get coupled? If I were to write the pressure P prime as a function of r and theta, and if I were to solve the wave equation, I will get something like P hat, which is the maximum value, into something like cos m theta, into I get the value due to the tangential. What happens in tangential? I get divergence, the radius keeps increasing, and what represents the divergence is the Bessel function, and therefore I get Bessel function of the order m into something like beta, which gives me my wave number, which is, let us say, combination of the tangential plus the radial into r by r divided by Jm, Bessel function of order m, into beta m into the value Jm beta m over here and beta ml over here, because I have both the waves together. And when I put the things together, I have pressure oscillations in this and this in this form, and therefore if I were to say yes, I couple both the tangential and radial together, I have at different places different values of pressure perturbations. This is in the combination of the first tangential and the first radial. Then the next one I show the first tangential, no, it is the second tangential and first radial, in which case I have different values, different places where I get the pressure perturbations are a maximum. Why did I show all this? The reason being, all what we are saying is I can get stationary or standing waves in a chamber, a rocket chamber, in which it could happen this way, it could happen tangentially, it could happen radially, and therefore there are some locations wherein I get antinodes, some locations wherein I get nodes, and if by chance I can excite these maximum values in pressure or maximum values in velocity, well, I can get a problem of instability. And therefore I will take this up in the next class, and we will try to gain a total understanding of what causes combustion instability in the wave mode and in different modes. Well, I stop here, maybe we continue with it later. Thank you.